Alright, hello and welcome to the Midterm 2 review. Everything that I write is going to be in the Midterm 2 review folder in our code from class. So let me cd into that. And I have a plan, but it will unfold as we go. So I want to get started with lists, and then we'll just work our way down all the topics that are on the midterm. In the list that I gave you. Okay, so let's start with lists, and I'm going to have a running example for every topic, but we're going to get to them slowly. So the first thing that we should do is talk about, I was trying to look up recursion tutorials for you guys, but I couldn't find any good ones, sadly. Okay, so just remember your big O stuff. We kind of hate everything that is bigger than n log n, is the idea. And yeah, we're going to be concerned with a lot of this stuff today. So I have taught you singly linked lists, and so that's essentially what I'm going to be testing you on in any coding questions. Maybe because you read about doubly linked lists in your book, I might give you like some multiple choice questions on those, but singly linked lists are where it's at. Okay, so let us get started, and let's have all these things in the back of our mind. So singly linked list, access, search, insertion. These are thetas instead of O's, but you can treat them like O's. And all right, let's get started. So I guess I'll just make this tiny. A linked list is made up. So we are off to a good start. My cat just fell off of me and scratched me up. Very good. Okay. So a list is made up of a bunch of nodes that hold values or keys, and then there's a next pointer. I hesitate using these arrows because they're not pointers really. This is just, I hope you understand what I'm trying to do here. So you can hold 1, 2, 3, of course, and the end of a list is marked by null, the null pointer. That's how you know you're at the end of a singly linked list. A doubly linked list would have a pointer backwards, but we do not have those in everything that we've implemented. So these are our singly linked lists. And so normally you're going to package up a list together with pointers to the beginning, or head sometimes, and then the end, or tail sometimes. I prefer to just call them first and last. So they're holding pointers to those nodes themselves. So if first lives at address 100, maybe this is like 212, this is 320. First holds 100, the address of the node. Last holds 320, the address of the last node in the list. Okay, and so then one's next is of course 212. 2's next is 320, and this null pointer is really just 0 secretly. Okay, so that's how you know you're at the end of a linked list. All right, so what can you do to a linked list is, I guess, the question. You can do all of these things. So you can go and search through something, or access a given node, like at index 3 of this list or something. And that is going to be linear time in the worst case, because you might want to access to the second to last thing, which means you have to go all the way through the first node. Like if it looks like this, it's a very long list, and you want like the second to last node, you can only get there from the front. You got to go all the way down to here to get to that second to last node. That's essentially O of n to get there. Yeah? And -1 operations to get there. So that sucks. Search, again, it's like look for a value. The value could be in the very last node, and you got to look through everybody. Insertion and deletion, this really depends on where you are. I think this is assuming it's at the front of the list. This really does depend, though. They say it's the average case, but it really does depend. In the worst case, these things, they say, are also O of 1, which is no fun. So let's see here. Inserting to the beginning is very, very fast. Okay? Do they have remove? Yeah. But they still say it's constant, yeah. So inserting from the beginning, at the beginning / end, is fast. So you can make a new node and put it right here. Oops. You can make a new node, put it right here if you wanted to, like make a 0 node. That's really fast because you have a pointer to first already. You can just make the new node on the heap, set first, set the next pointer. Everything's fine. That is easy. Same with last, making a new node over here, like maybe the 4 node. It's like, yeah, this is now null. The old last's next becomes boop, just like that. That's fine, and that's fast. Just make a new node, set some pointers around. The issue lies when you want to set something equal to like the second to last node. Okay, so that takes some time because you got to go through the list to find the second to last node to set its next pointer. You see that? So if you want to put a new node right here, I got to go all the way to the end of the list to get there. That's no fun. Okay. That's O of 1. Inserting in a random place in the list, though, in the worst case, is O of n. Okay. Deletion. You want to get rid of a node. It's very fast to do it for first. That's not a problem. You can just remember it's next and be like, okay, that's a new head. Deletion is constant for a singly linked list. Deletion from the front, that is constant. Deletion from the back, though, is no fun because you're getting rid of this node at the very end of the list, which means you need to go and find the second to last node. And we talked about how to get there. It's a long journey for your node pointer. That's no fun. So deletion at the end is O of n. And it averages out to be n over 2, which is n. Okay? So that is no fun for singly linked lists. Doubly linked lists, it makes it a bit easier. Yeah, so that's insertion, deletion. We talked about search. I think these are the one cases where this website is wrong. It doesn't know, well, depends on the insertion and deletion, that is. So maybe it thinks it's only at the beginning. This is where it's not true. Okay, so just keep this stuff in mind and you are golden. So those are lists, and now let's build them up in code, okay? Because what use is all these diagrams if we can't talk about them in code? So let's do lists. And so I'm not going to make a list class, but I'll make a list struct. So each node of a list has what? It has data, which can be of any type. I'll just use ints because that's me. And alternatively, you could use like chars, doubles. You know how to make this a template now, but we won't go there yet. Okay? And then it's node star next. So you're pointing to yourself. Okay? It's a recursive type. All right, so if I want to make the list 1, 2, 3, I'll make those nodes. I don't have to make them on the heap, but I will. Node. I'll do the same for 2 and 3. So I'm trying to make this list right here in blue. Okay. So 1's data equals 1. 2's data is 2. 3's data is 3. All right, and then the next pointers. 1's next is 2. 2's next is 3. And 3's next is null. All right. Fun stuff. So that is the list. 1, 2, 3. Let's add 1 to every node by printing out, or by iterating through the list, and then we'll print it out. Okay. So I'll use a while loop for this one, for this first iteration. So I'll make my node star cur node maybe, start it at the front of the list, which is 1. Now maybe we can keep track of it like we would do in a normal list. in a class. So front is 1, or first, I guess. Last is 3. So let's say this. There. So I can say first, like we would normally do. All right, so curNode starts at the first node, and while curNode has something in it, it's not equal to the null pointer, I want to modify that node, adding 1 to the data. I'll be like curNode data plus plus. This will work. Just to be more pedantic, we can say curNode data plus 1 or plus equals 1. Okay. And then, of course, we need to advance our curNode pointer. All right, so we'll say curNode equals whatever it was. It's pointing to a certain node. Go to the next one, the one after it. Okay, so this will make everything 1 more than it was. So those original variable names don't make sense anymore. So now this is 2, now this is 3. Now this is 4. Okay, then let's print out the list. So 4 node star n, I'll use a for loop this time, equals first node star n is unequal to null pointer. Oh, sorry, I don't have to redeclare it. N is unequal to null pointer. How do I advance it? N equals n next. So I'll see out n's data and maybe a space. All right, so this will add 1 to everything in my list, and then we'll print out everything. So there. It's faster to just do that. Two, three, 4. Beautiful. All right, so that's lists in a nutshell. Time for templates. So there's my example. We'll talk about it in a second. So a template can be a function or a class. And that makes it work for anything, any type. Usually it's a type. It could be values as well, but we won't get into that in this class. Okay? A class or a function can be templated. That makes it work for any type that you give it. Okay. So like the default example is, I don't know, that min function. Like, I don't want to write 50 different min functions. Int x, int y. So if x is less than y, return x, else return y. And then I want to do the same thing for strings, or doubles, or floats, or whatever. Or maybe I have my own made-up class called c, min, cx, cy, dot, dot, dot. Same stuff, same code, same body. It works the same as long as there's a less than operation implemented. Well, screw all this. Let's make a template. We can say template class t tmin tx ty. I can be like return x less than y question mark x colon y. Beautiful. And then suddenly this can turn into every min function you would ever want. It'll be used to create this one. It'll be used to create this one, as long as somewhere in code you call it on ints. Somewhere in code you call it on C's. Okay? It's going to generate the code for you. It's beautiful. And this process is called specialization. And so that in a nutshell is templates. And now I'm going to give you an example after I go and stop my cat from chewing on my iPhone cable. All right, we're back. Let's make this work. So I'm going to make a templated double functions. Oh gosh, I can't make it called double, can I? Let's say I'll call it dub. Okay? And that'll add a value to itself, so it'll work for like ints and strings, and then I'll make a doubler class that wraps around this functionality. So I'll show you template classes and template functions, one after the other. So the first thing that I want to do is make a dub function, not double because that's a reserved keyword, of course. That'll do the following. It'll be like cout dub, I don't know, 42 please. Work on ints. Cout dub hello. Work on strings. Same function doing these things. So it's going to be template class t tdub tx, I guess. And so what it's going to do is it's going to return x plus x. Okay, that's going to be my function, and we're going to hope that it is going to eventually work. And I notice my error already. This has to be a string to use the plus operator. Otherwise, it's a C string. It's a constant C string. Okay, so now I'm actually giving it a string, giving it 42, and this will work. It'll just use the plus operator on whatever type t I have used, and it's going to work just like this. So I could be explicit. I could say dub int, okay? Could be explicit, or C++ can infer the template parameter. I guess it's template argument. So I guess at the end of the day, I want you to think about templates as like functions at the level of types. This is like a type level function now, okay? Suddenly, min doesn't just take an x and a y, it takes a type as well. It's as an argument to it. Like the min function takes a type as an argument now, and it gives you back a function that works on that type, if that makes any sense at all. Otherwise, forget about what I just said. Think of it as a type level function, okay? That takes a t and gives you back a function, in this case. Because that's essentially what you're doing when you're using templates. You are instantiating the template parameter with your template argument of a certain type. Now I have a double function on ints. Now I have a double function on strings that's inferred the fact that I need the string here. Okay? And so I get back 84 and hello, hello, because those plus operators are implemented differently across types. But all I needed to do was rely on the fact that there was a plus operator that existed, and suddenly this function works just fine. Okay? So that's templates for you. This code gets generated, like it made the int function, it made the string function, it replaced the t somewhere deep down in code. But we don't need to care about that. As implementers, we just make one function that works the same, no matter the type. Okay, so that is templates. For functions, let's make a doubler class that essentially does the same thing. So it's going to be template class. It doesn't have to be t. It'd be like type. Why not? And it's going to be class doubler. And it's going to have as a private member variable a something of the type type. That might get confusing. Let's call it like u or something. Something of the type u. Let's call it x. The thing we want to double. Okay. And so then we'll have our member dub function now, I guess. Tdub tx and well, let's just include it like this, but it's not t anymore. Remember, it's u. That's the variable. That's the parameter for this class now. Okay. And so, in essence, we can make a constructor where we give it something of the type u, and this can actually just be a member function that doesn't take anything. And this should work, I think. Yeah. So let's implement these two methods, the constructor and the dub method. So here's my idea. Okay, so for this one, we can just be like, okay, my x is the x that I just was given. For this one, we can be like, okay, I'm going to do everything the same. Return my x plus x. I just doubled whatever my x thing was. Okay? Oh, and I'm sorry, it's doubler t's doubler. Excuse me. And excuse me once more because I accidentally said t instead of u. So, yeah. The name of this method, it's the constructor for doublers, but it's the constructor for a special kind of doubler. A doubler specialized to the type u. Okay? This is the dub function, the dub method on a doubler of u class, because it's going to make a separate class now every time we use a doubler for a different type, if that makes any sense at all. Okay, so I can be like doubler dint and give it 42. I can make a doubler dstring and give it hello. Okay? So that's what I want to do, and this needs to be string, and it's going to require template arguments because I don't think C++ in this version of the language is fancy enough to do it. No, it compiles for me because I guess we're using C++ 17. It's quite possible that whatever I'm using inside of my editor is not set to C++ 17. But here's the fast answer. We can be like doubler int, doubler string. Okay. Technically, you don't need that for later versions of C++. G++ was happy. So this will compile, and then we can do the same thing. We'll be like cout dint, please double your int that I put inside of you. And same thing for string. Oops. Okay, so suddenly we have a class that works, that has the same methods that do the same thing, just when the types are different, we get different functionality. Okay, so the same thing, I've just made a wrapper around that to show you template classes now. Okay, so I hope that makes sense. That's templates in a nutshell. Stacks, queues, and Deques. So time complexities of these are interesting, but just at a high level, remember what you got. So a stack is just what we know and love. You have, there's a concept of the top of the stack, and so every time you push something, like here's the 4 is the top, then I push 32, 32 is the top, I push -1, -1 is the top, and when I pop or get or peak, I can only ever look at the top, okay? This is the top, this is all I get to see. And of course I can pop it. And then I'll be able to see 32 because that'll be the new top. Okay, so that's stacks. Queues, of course, is essentially the same as stacks, only the end on which you pop is not the same as the end on which you push. So you got the concept of a front and a back or a rear. So the front of the queue is where things get peaked or popped, okay? And the back is where things get pushed, okay? So pop from the front, push from the back. So it's like people waiting in line. The people in the front get serviced first. So this is push to top and pop from top. Okay. So that's the main difference between queues and stacks. Not bad at all. And then Deques are just like a combination of the two. Like you have the ability to look at the front and the end and add to both sides. So like a deck. I'll use 2 arrows, I guess. Like 1, 2, 3. You can access both the front and the back. Okay? You can push to and pop from the front and the back. Okay, and all this stuff deep down under the hood is going to be very fast, because usually we implement this stuff using a linked list. So, for example, here is stacks and queues. Normally we don't even have accesses or searches, they're just trying to keep the same words, but really we have pushes and pops, okay? Insertion and deletion, and those are the same in the worst case and the best case. So it's constant time for all that stuff, okay? It's beautiful. So you implement using a linked list usually. So for example, the stack, this bad boy is going to be translated into a list that holds like maybe the front of the list can be the top of the stack, because you know that you can immediately push and pop to and from the front of a normal linked list immediately. Okay, and maybe for a queue this will be represented again as the list 1, 2, 3, so that you can pop from the front and push to the back. Those are, again, constant time things, even on a singly linked list. Okay? The deck, though, if you want this to be constant, you need to use a doubly linked list, because you can pop from the back now. It needs to be a doubly linked list so that it's not linear time to find the second to last item. Okay? So, need doubly linked list here. For constant time. Okay, but usually you can think of it as everybody, all these operations, always constant time. Beautiful. Okay, so that's stacks, queues, and Deques. Let's reverse a vector with a stack now. And then I'm going to reverse a queue with another queue. And Deques, they're just a combination of the two, so I'm not going to demonstrate them in code. So let me use C++'s built-in stuff. Okay, so vector, stack, queue. So the first thing I want to do, reverse a vector using a stack. So I'm going to push all my stuff. I'm going to push my 3, 2, 1 in order, or 1, 2, 3 in order. And then suddenly the order in which I pop them off is reversed, right? So stack int s, so for int x in v, s dot push x, so put everything into a stack. And then pop the stack to reverse v. So I guess the idea is we got to make a new vector. vrev we'll call it, and we'll say while s is not empty, well, we're going to push what's on the top to the back of this new vector. And then we're going to pop. Okay, and eventually s is going to be empty, and we're done. All right, so for int x in vrev, let's go ahead and see out that. and hopefully we see 1, 2, 3. I guess I didn't have to make it like this. I said one thing and wrote another. So for it to match this, it had to be 1, 2, 3 in order. So let me just make it like that. Okay. So now we have stacks queues. 3, 2, 1. Beautiful. Okay. So that's working good. That is stacks. Let's now do queues. This is going to be weird. So I want to reverse a queue with another queue, which is going to be interesting. So let's make a function for this, because this is going to get really weird. Queue of int, reverse, queue of int, queue that I'm given. Dun, dun, dun. And yeah, we might as well just copy it, because we don't want to mess up it. Who gave it to us? So here we go. QRev is the queue that we will make. So this is going to be a bit tricky. So eventually we're going to return QRev. But the idea is, so initially, for example, we have like here's our queue 1, 2, 3, and we need to somehow discover the 3 so that we can push it to the end of the reversed queue. So it needs to be, we need to get the 3 out somehow. So the idea is we need to find the end of the queue, okay? We need to find the end of the queue. So we need to, in essence, swap things around. I need to know when 3 is at the front of this queue, okay? So the idea is, algorithm, I want to use the size of the original queue, which I can get, that's a member function. Push and pop until the last thing in the queue is at the front. So I'm going to turn this 1, 2, 3 into 3, 1, 2, because I'm going to immediately pop and push 1 and 2 to the end. Do you see that? So that's how I'm going to get the 3 at the front. Yeah? That's what I want. So I'm going to keep on doing that. Okay, so I have to do this whole thing queue size times. So round 0, round is less than queue dot size round plus plus. So that's how we'll do it. And so what I want to do now is going to be can I? Yeah. So now I need to go through this queue n-1 times. To shuffle that end to the beginning. I need to do this. I need to pop the 2, or pop the 1 off, and so then it's 2, 3, and then immediately push the 1, okay? Then I need to pop the 2 and immediately push the 2. So n-1 times I need to do that, play that game. So it's gonna shuffle around things until the 3 is at the front. So for int I equals 0, I is less than queue dot size -1, so do it queue dot size -1 times. Immediately queue dot push, queue dot front, and then queue dot pop. Okay, so this will do that. It'll take 1, 2, 3, the queue, turn it into 2, 3, 1. Yeah. And so once this loop ends, the last element is at the beginning. Okay. Add the front to QRev. Okay, we can push it now. So suddenly QRev has just 3 in it, because I found the 3. Then I'll find the 1. Or then I'll find the 2, sorry, because that'll be at the end now. I'll do the same process, and then I'll find the 1. It's not really important for you to understand exactly what's going on, just that I'm using queues in fun ways. Okay, so QRev dot push q dot front now. And so I'm going to do this size times 1 for each element. I'm always going to get the last thing by playing this game, n-1 times shuffling things around, then pushing things, and then in theory this q that I have that I get back is going to be reversed from what I was given. So let's see if it's going to work. So q int q dot push 1, 2, and 3. So now I have my q with 1, 2, 3 in it, and I'm going to try and reverse it. So reverse q, and then let's go and print it out. So while QRev is not empty, I'm going to see out the front, and then a space, and pop it. And then I'll see out a new line. So I sure hope that we see 1, 2, 3. There might be a bug, in which case I'll just stop the video, go and fix it. But oh man, did it work. So it was all, this was the main way that we did this. That was the reason this worked. n-1 times we shuffled things around. We made the 1, 2, 3 queue into the 2, 3, 1 queue into the 3, 1, 2 queue, and suddenly the last thing was at the front. It's so beautiful. Okay, so this is very inefficient. It's horrible, but you end up reversing a queue using a queue. All right, you did not use a stack in this case, which is hilarious. But it runs into, like, this is an n-squared algorithm because of that. You see that? Oh no. But fun stuff. All right, so that's my example there. And I'm sorry, this is probably going to be a very long video. You're not required to watch this. Please like fast forward to where you need to go. But I am trying to give you as much as I can give you. Okay, hash tables. My example is going to be taking names to phone numbers. We'll talk about time complexities, of course. But the idea is, the idea of hashing in general is, I have some random blob of a type. My type is t. And I want to store that in a lookup table. So indices of lookup tables are numbers. I need to somehow take a t and turn it into a special number, okay? And the way that I do that is through a hash function. I have some hash function that takes some type t and always gives me back an integer. Usually it's a positive integer. Or non-negative, that is. Okay, so that's what a hash function does. It just turns some type into a number. That's all it does, so that we can store it in a lookup table. Because then I can take, like, hi mom, and suddenly with the right hash function I can send that to 42. And, like, my name can be sent to, like, I don't know, 27. Who knows? We just make large numbers based on a given type, okay? And then we shrink them down to fit in our table, okay? Usually using modulo, you do this. And I encourage you to keep reading your book some more, because it talks about, okay, you need to use primes. These are some good hash functions, things like that. I'm just going to give you the high level right now. That's all we really have time for. So the idea is, based on this fact, we can go from a number to an integer, any type, a string, you name it, a double, just to a plain integer. We suddenly know where we might put these things. Okay, we can store key value pairs. Okay, so that's all a hash table does. It stores key value pairs. It's beautiful. Okay, So normally, the one that you implemented in your lab, it's using open hashing, but closed hashing is also a thing. So let's talk about both. So for open hashing, you use a list. So there's always this underlying lookup table with that takes numbers, indices, to values of any type. So maybe I want to store hi mom and Lawton and, I don't know, blah equals 87. And, or actually, let's make them both 42. So here at index 27, we can store Lawton and its data. So my name and its data. And then also at index 42, well, now we have the problem. Okay, so how do we handle clashing things? And your two options are open hashing and closed hashing. If you have a clash, you'll have to store a list for open hashing, okay? So at every index, even if it doesn't overlap yet, you're expecting it to eventually overlap. So you say Lawton and whatever, and this is a list right now, okay? So at index 27, this is index 42, you store a list, okay? Whee. And really I should be writing 27 in here because that is all this is. This is a number. 27, 42, these are indices into my hash table, my underlying table. And so the first one, like maybe it's hi mom, and then the second node can be blah, if that's the order in which I insert these things, and then it's null. Okay, so open hashing is you use a list to resolve conflicts. So your hash function, you ran it, you got a large number, you shrank it down using modulo or something to the size of your table, but you still had numbers that clashed, indices that already held something, so you store these things in a list, okay? So for both open and closed hashing, you need to store a key value pair. For open hashing, it's like, well, yeah, you got to index 42, but which thing were you looking for? Were you looking for the data associated with hi mom or the data associated with blah? You tell me. So you need to save the key because otherwise you don't know like which one of these nodes you were really looking for. All right, so that's open hashing. Closed hashing uses the table itself, okay? To resolve conflicts. It uses another index in the table. And it has another way of solving a question, like which index do I try? Because I'm going to try a different index now of this hash table, or this lookup table, on attempt I. Okay, so I originally, maybe, I don't know, let's just be blank. So again, let's use these examples. Great. So originally, I wanted to, I was able to store, let's do it in this order maybe. Hi mom, Lawton, and then blah. Let's insert these things into our hash table. And here's our hash table. So it takes indices, numbered indices, to actual key value pairs. And so hi mom gets inserted at index 42, its key value pair associated with it, and where this is the key. So we go to index 42 in the hash table, and we're like, okay, it's open, so I'm going to store hi mom and the data associated with it. Cool. Then at index 27, we'll store Lawton because that is open at the moment. This is an empty hash table. Lawton and its data, we've got space, and then we try to insert blah and its data. That first brings us to index 42, but now we're screwed because we cannot put anything there, okay? We need to try a different spot. And the different spot is guarded by these different kinds of probing strategies. Okay, you can do linear probing, quadratic probing, and double hashing to figure out where you should go. So the first time you're always going to try, where h1 is h in this example, you're always going to try the original spot. So I starts at 0. It's attempt 0 right now. Let's try the original location that we were hoping to put this thing. That's not going to work. So, and these are all like mod table size. So let's try this index, and no, it's not going to work. So with linear probing, we're going to try right here. Okay, so linear probing is always going to go to 43. That's the next spot. And it's actually open. If it's open, it'll store it. If it's not open, it won't store it. Okay, it'll keep on looking like to index 44 or something. So that's linear probing. It's very easy. It's very clear to see where the next place is to look. Quadratic probing, you have to choose two numbers. C1 and C2, it doesn't matter what they are. Well, it does kind of. But as long as you choose them appropriately, it'll just make a new index for you to try. And this index doesn't crowd any place because it's getting spread across these I-squareds, these i's, and things like that. So first, like if C1 equals 3 and C2 equals, I don't know, 5, the next place to try after this for 42 and a special hash table, let's say the size of the hash table is, I don't know, 55. We wanted to originally go to 42 because that's what the hash gave us. So we try 42 plus C1 times 1 plus 5 times 1 squared. Okay, and if that one's not open, we'll try 42 plus 3 times 2 plus 5 times 2 squared, because I is now 2. It's my third attempt. Okay, so these always get advanced. And so you see it won't crowd any place. It'll just like start jumping around because I is huge, or I squared is going to eventually be huge. And it'll just keep on wrapping around. Okay, so that's linear probing, and this is quadratic probing. Quadratic probing sequence. And then double hashing is like, okay, it's the best thing you could do because it's got the most randomness in a sense. You just use a separate hash function. So it's like, originally I'm going to try the first index, index that I was sent to, like 42. If that doesn't work, I have a separate hash function that does something different with my t. Like I got hash 2. That also takes a t to an unsigned int, but it does it in a different way. And so each time, for each value, it gives back a different number, and that is beautiful because it's going to shuffle it around in a very nice way. Okay, so like double hashing h1 of blah took us to 42, but maybe h2 of blah takes us to like 37. Yeah? So then we're then going to try index 42 plus 1 times 37 on our next attempt. If that one's used, then we'll try 42 plus 2 times 37. Yeah? You see that? So this value depends on the hash function on the actual key you're looking for, which is beautiful. So I know this is a lot of words and it's getting complicated, but I encourage you to read the book over again if this is getting to be a little too much in words. Okay, there are pretty examples there. So that is double hashing, and now, so my example is going to be taking names to phone numbers. Okay. And of course, we're going to use unordered map for that. Boop. It takes strings to ints. And we can insert things. So it's using its hash function on strings that the C++ library knows about. It's like, all right, put Lawton at there, and then like put my mom at one more or something. And so suddenly we have a phone book and we can look things up. Okay, and we can see if something's there. Like, does it exist? You can use count for that. guess I should have called this unordered map. Okay, so it finds my number, and it knows that a key doesn't exist for Dad right now because I didn't put that in my phone book. Okay, so that's that. I think I should call this something else. Map.cpp, let's call it unordered map.cpp. Okay, so that's good there. And let's move right on down to trees now. So in code, we're going to build up a tree and just go and print it out. But first, let's remember our terminology. So our treemonology, I guess. You got, in a binary tree, a root and then a left and right child edges. Okay? So you can hold keys and values at each node of a tree. There are nodes again. And in a binary tree, you can go left and right. But a tree, in general, can have as many children as you want. So this is a tree. It's not a binary tree. Okay? And so it's got keys at each node. There are edges that you can follow to each child. We don't really talk about siblings, but at the very bottom of the tree, you have leaf nodes. Those are very important. And each node, except for the root, has a parent always. So there's those pointers. You have a height of a tree, like how many levels do you need to go down to get to the lowest leaf node? That's the height of the tree. And there's a concept of levels, like every node at height 0 is level 0. Every node at height 1 is level 1, etc. So that's really nice. And then remember, you have balanced trees. And like there's complete, there's balanced, there's perfect. I encourage you to look those up in the book. But the idea is balanced trees aren't like aren't too side heavy. So this is like really unbalanced. This is essentially a linked list at this point, whereas this one is balanced. Okay, and balanced trees have height on the order of log base 2 of n. Okay, you don't have to go down too far to ever get to a leaf. Okay, I hope that makes sense. So that's tree terminology. Balanced trees are super nice. And yeah, all the operations on trees are pretty fast when they're balanced. Okay, so like a red-black tree is a balanced tree that you read about, and everything's log of n because everything depends on the height of the tree. Like that's how long it takes to do things. If you don't have a balanced tree, you're kind of in a bad place because suddenly you have it doesn't even have it here. Suddenly you have to do the height of the tree to get places. So we'll talk about all the operations right after I remember that hash tables I didn't talk about the time complexities for. So for a hash table, everything on average is going to be constant. Search, insertion, deletion. Constant, on average. You'll eventually resize the table as well. So every operation is constant, but things can go bad if you have bad hash tables, or if you have bad hash functions, or if you have very small tables with lots of key value pairs. Like you'll have way too much overlap on that point. Because like if you had a size 1 table, everything gets mapped to that one index and it's just a linked list at that point. Okay, so it's going to be linear. Okay. And then my writing got out of the way. Let's just keep it like that then. You'll be able to read this once you download it. Okay, back to trees. So yeah, the tree operations now. Again, don't really have anything here. But the tree operations are going to be like searching, insertion, and deletion, things like that. All right, so let's talk about those for just a general tree. If you want to search for a node, like this is 1, 2, 3, 4, 5 or something, For a general tree, oops, this is no fun. So if it's not a BST, you have to like search everywhere. Like you have to try every possible node because you don't know where this thing's going to be. So it's going to be O of n. To add a new node somewhere in the tree, just wherever you want to. In the worst case, you need to go down to a leaf, and the leaf is going to be height levels down. Okay, so that's not too fun either. So it's O of h for a lot of things. Okay. We're going to eventually talk about tree traversals, and all of those visit every node. So those are all linear in terms of the number of nodes, which is not a big deal. But yeah, we don't really talk about trees, tree trees, usually, in terms of it, like insertion, deletion, and search, because like, where do you know to put these things? So we'll save a lot of that for when I talk about BSTs. But the idea is, if you know where you want to go, if you know, I want to delete this node right here, for better or for worse, it's essentially constant time to do anything. Like if you have a node in mind and you want to insert like a new subtree starting here, like a new node, you can do it pretty fast. You just need to like pick who you want to be the parent, things like that. We didn't really talk about this because it wasn't a BST. So normally, if you're using a normal tree, you're just probably traversing it somehow, like we were doing to like solve the height stuff, to evaluate those expression trees. So normally it's going to be a tree traversal, which is going to essentially visit every node. So O of n for those things. Okay, so those are just tree trees without any properties on them. We know that we have BSTs that make things a bit fancier. But first, before we get to BSTs and their complexities, because they have real nice operations that we use, let me do this example where I build up a tree and then I print out each node. Okay, without doing a traversal yet, because we're going to get to recursion down here in a second. I guess I could use recursion. Why not? So every tree node looks like this. So struct tree node. Technically, you don't have to save the parent pointers, but it's a good habit to get into because we're going to eventually talk about BSTs, and they'll have the same struct in that case. There's always data. Okay, that's how you. That's what you put in the tree. You can also have a value that's separate from the data, but I guess that's not really necessary for us right now. But you could put something else. Okay, so there's like a key and a value. I called it data in the lab, I think. And then you need to know your left, right, and parent pointers. So the left subtree is indicated by tree node star left. Tree node star right tells you how to get to the right subtree. And then your this parent is not a subtree anymore. It's just like another node. Who is your parent? All right, so let me make the tree that looks like this. Let me make one. This is going to get interesting. 1, 2, 3, and then maybe 4, like that. So tree node 1 equals new tree node. So 1's key is 4, and 1's val, that can just be some random string, and I'll use that the same for everybody. Okay. 1, 2, 3, and 4. And then we have the left-right pointer. So 1's left is 2, 1's right is 3, 1's parent is null because it's the root. 2's left. All right, let's do everything that's not null right now. 2's right is 4, and then everybody else, like 2's left equals 4's left equals 4's right equals 3's left equals 3's right, all equals the null pointer. Okay. So that's all well and good, and now parents we need to work on. So 4's parent is 2. 2's parent is 1. Right? Yeah. And I can't talk and write at the same time. 2, 1, the pointer. Okay, I think that's gonna work. And then now we have this tree, and we can go and traverse it. So how do we print out every node if we know where they all are? Well, we can do the following. Let me copy this down here so I can see it again. We can do this. We can say cout, well, 1's the root, or maybe I can make a root pointer. Just to be extra fair. Nobody's singled out, we gotta go through the root. No, and it's key, sorry. Root key. Okay, so that's the 1 node. Where is the 2 node? It's root's left. It's key, apostrophes. Where's the 3 node? It's root's right's key. Where's the 4 node? It's root's left's key. Sorry, it's root's left's right's key. I hope that makes sense. It's like, okay, starting at the 1, go left, then right. Then get the key of that node that you just got to. Yay, so it works. And I think I set up the pointers properly if you want to use this to practice your traversals. So those are trees. Now let's talk about BSTs, and then we'll talk about recursion. Okay, so BSTs are special kinds of trees. Remember that BSTs respect the BST property. The left subtree, all the values in it are less than the root's key, the root of this particular subtree, the parent's key, and all values in right subtree are greater than the parent's key. You can make this one of those sides less than or equal to or greater than or equal to, but I'm just not going to have duplicates in my BSTs. I don't like them. So here is a nice BST. I don't know, 50, 25, 12, 13, 75. No, sorry. Definitely can't have a 13 there, can we? Let's do like 33. So everybody in this subtree is smaller than 50, bigger than 50, smaller than 25, bigger than 25. Okay, so we've respected everybody, and yeah, that's a BST. Let's talk about the time complexities. So if you want to insert, it's going to be O of H in the worst case. So this is worst case time complexities, because depending on where you want to insert, like maybe it's 32. You got to go right, left, the opposite of what I just said, left, right, left again. So you need to get to the smallest element. You need to get to a leaf node. And that will take O of H time, where H is the height of the tree, because you might have to go down the farthest branch if your tree is very unbalanced. Okay? So because of that, we say O of H, but O of H becomes log n. and you read things, you read about how to potentially make a binary search tree balance, but I will not test you on those things. That's for an algorithms class. Okay, so insertions O of H, because you need to go down to potentially your last level to insert the next node, like 32 or something. That's the idea for that. So that's insertion. Boop. And, okay. Insertion also requires search, so we should talk about that too. Search is again O of H because you might be searching for the thing that is the lowest in the tree. So that is the height of the tree. Oops. So again, like maybe I'm searching for this 32 that I just inserted. I gotta go left, right, left, and that is the height of the tree, 3. Yeah? And I need to make a comparison at each node. So at each node I'm doing constant work. And I'm visiting h minus 1, or h exactly nodes. Yeah? That's the idea. So search O of H, and then insertion is just search to figure out where you need to insert, and then actually make the node, which is still constant. Okay, so that's insertion. And then deletion. This one's fun. Remember this. So, dun dun dun. Deletion is going to be the following. I think, let me just show you all the cases. So this one's really fast. It is constant. If you're trying to delete a leaf, or if you're trying to delete something with just one subtree, then you can just bring it up, manipulate some pointers. But things get a bit weird when you need to do 2 subtrees. Okay, the 2 subtree case requires finding either the predecessor or the successor, and that is going to be O of H time. So if you have a pointer to the node you want to delete already, like you already did the search, and you don't have to do it again. But if we're talking about worst case, there are 2 children. That's the 2 children case, and you have to find the predecessor or the successor, which involves an O of H amount of work. Okay, and then you can do the deletion in one of the other 2 cases, which is then constant after that. But usually we're searching anyway. So deletion will always be O of H. Okay, so hopefully that made sense. Please yell at me in office hours if any of this is confusing. Do take advantage of the office hours before this midterm. Okay, so that's the idea for all of those things. O of H, O of H, O of H, and if the BST is balanced, these suddenly become beautiful. They become log n, okay? So the average case is the worst case for those guys. It's so beautiful. B tree, red-black trees, AVL trees, same properties. Super, super nice. Okay? So yeah, BSTs are very nice for holding key value pairs when you want to order them eventually. Okay, you want to get the order of the nodes. If you don't care about order, you just use a hash table. And yeah, that's the idea there. Things do get a bit wonky. You might, I think I've assigned you to read about B trees as well, and like your file systems in your computers are stored using trees, not just hash tables, so they are good for other things. So that's BSTs. Let me give you an example of manually building up a BST and then making a search function. So I'm going to remake this search function for you. So let's try to make this first blue tree. I'll try to do that in code. So I'm going to have to go back and forth, so sorry for that. Let's take most of this. Let's just take all of it right now. I want the tree nodes all of this, please go away. So this is probably the case where you're going to want to either pause the video. Actually, I'm going to pause the video for you while I make this tree, okay? You don't have to watch me make it. All right, I've gone and made this tree now, the blue tree, 50, 25, 75, 12, and 33. I believe it's all correct. And then the root is going to be 50. So I want to search for, let's say, let's search for something that's there and then something that's not there. So search for 33 and then 32. And so search will return a pointer. So we're given the root of the subtree and then the key value that we're looking for. Okay, so this is the idea. We're going to start at the root. So starting at the root, and then go left and right depending on whether or not we're looking for which kind of value. So if the value that we're looking for is smaller than our current n's key, we're going to go left. Okay, so n starts out being this guy, and then eventually n's going to be set to be this one because we're going to go left, then it's going to go right, and then we're going to get potentially to null. Okay, so that's what n's going to do. I guess it starts here. Starts at the root. Okay, so let's say while n is not equal to null pointer, let's do this. Let's be like, okay, if search value is less than the current node's key, or I'm calling it data here. I changed it to be data. So if it's less than the data that I'm currently looking at, so it's like I am looking for 32, I see 50, so 32 is less than 50, I'm going to go left. N equals n arrow left. So I'm going to advance n to be the left child. So n becomes, I'm going to start searching at this subtree now. I'm going to start searching at this subtree. Okay? That's the idea. Else, if the search value, the thing that I'm looking for, is greater than the current node's data, I know I need to go to the right. Okay? And then else, we found it. So I'll return n in that case. And so if we were sad enough to get here, we hit a leaf because we hit n being null, and we try to go past a leaf because now n is null. So still return n, but n will be null. Alternatively, you could just say return null pointer. Okay. So that's the idea. Let's search. Let's see it in action. Hopefully it makes sense to you. And let's see if I have done things weird. Like maybe my pointers were off, because it was manual the way that I did this. So okay, we found the 33, and we could not find the 32, which is perfect. Okay, I can trust that. So that is BSTs in a nutshell. Lots of information there. Please review the videos for all the algorithms for these things. I definitely do not have time to go over all of those. That's for sure. This is already getting quite long. Okay, finally, recursion on trees and lists. So in either case, like we're going to do trees first because it's fresher in your mind, but I'm going to start with an example of lists. If this is your list, like L starts at, front starts at 1, 2, 3. Any recursive algorithm just needs to get called on a smaller thing. And normally, for these data structures, because they're recursive in a certain sense, these data structures themselves have lists inside of them. So here's a smaller list. So you can make a recursive call on that and guarantee or assume that it's going to do the correct thing. And it's guaranteed to do the correct thing if you build up the answer correctly. Okay? Let's confirm this is still recording. Yes. And okay, so in trees, you have a root. Usually we can do this with BSTs. I'm going to do it with BSTs. Like we had 50, 25, 75, 12, and 33. Well, from the root's perspective, there are two smaller subtrees, are there not? And you can make recursive calls on those. And you can assume that they do the right thing for you. Okay? So, I'll remember to say that a little bit too. So here's the left subtree, here's the right subtree, and you can make recursive calls and assume that that it does the right thing as long as you build up the answer correctly and implement the proper base cases. Okay, so let me give you some examples of recursion on trees first. So let's search for something in a tree, and let's make this not a BST. So this thing could be anywhere that we're looking for. Okay, so I'm going to add that into the trees.cpp file. Okay, so I'm using this tree now. Let's search for the value 4 in this tree. Okay. And this is going to be a bit different. So this is why I'm giving this example. This is not the BST search. So let's just say bool search, starting from a root of a subtree for some value to search for. So this is going to be recursive. The idea is this value that I'm searching for, it's 1, 2, 3, 4. I have no guarantees over where in the tree it could be. Okay, so I start here. Here's my root. I don't know where 4 is because this is not a BST. Okay, pretend I have not seen this tree before. I don't know if the 4 is in this subtree or the 4 is in this subtree. I have to try both. Okay, so I have to search here. Search here as well. Okay, so recursively, try and find the 4 in a smaller subtree. Okay, that's the recursive case. And eventually, it's going to work its way down the tree, and I really want you to come to office hours if this recursion stuff is not making sense still. Eventually, it's going to work its way down the tree, and it'll get back, like, it'll get called on empty trees. And you never have what you're looking for in an empty tree because there's nothing there. Okay, so that's your base case. All right. So in the recursive case, after you make these two calls, because the 4 could be here or here, there's one place that you haven't looked, and that is your root. You have to check that as well. Okay? So the recursive case guarantees that it'll find it if it's in the subtree. You just have to build up the final answer by looking at your root. Okay? So here we go. Recursive search for a non-BST. So if the root of the current subtree that I'm looking at is null, so that means it's an empty tree, return false. There's no way we're finding x in an empty tree. Otherwise, we'll do the recursive case. So return, well, maybe it's in the left subtree. Or it could be in the right subtree. Or it's my current node. It's root's node. Okay, so one of these three. and it's recursively going to do it right. Okay, and sorry, it's search all these things for the same x. Okay, I hope that makes sense. So you're making recursive calls and you're immediately using them. I could save them in intermediate values, but that just clutters things up. It's like, okay, search left, it'll return true. We get to assume that recursion is going to work for us. It'll return true if it finds it in the left subtree. If it wasn't there, we need to search the right. And if it wasn't there, we need to worry about a root. That checks the entire tree recursively, okay? Okay, we get to assume that the recursive calls work as long as we build up the final answer. And what do you know? We found it. True. Let's search for something that's not there, like 5. And we get false. It's not there. Okay, so that's BST. Or, sorry, non-BST search. And then let's recursively delete a tree. Or BST. It works for either one. Okay? So recursively deleting a tree means recursively delete the left subtree and the right subtree. We can assume that it's going to delete them properly. And then what's the one thing that we haven't deleted in the recursive case? The root node. Okay? Let me draw that in like red or something. It's like boop, thin red, boop. Recursion gets rid of these. Recursion, you can assume, will correctly delete the subtrees. All the subtree nodes, and then it's your job to delete the root. That's your last job in the recursive case. And again, empty tree, there's nothing to delete, so that's your base case. So it's usually either empty tree is your base case or like single node leaf is your base case. So delete a tree starting with a root pointer. So the idea is if root is equal to the null pointer, there's nothing to delete. Return. Do nothing. Otherwise, we have some stuff to delete. Recursively delete the left subtree. Recursively delete the right subtree. And so now everything's gone except for the root of this current subtree we're working on. So we have to worry about deleting that. And then we're done. Okay, that'll delete the entire tree recursively. And I'm not going to get any output, but if you ran valgrind, it would be happy here. Okay, so that's deleting stuff in trees and BSTs. Let me show you, let's do tree traversals before we stop talking about trees. So remember your pre-order, in-order, and post-order. They involve, like, in some order, visit root, visit left subtree, recursively visit right subtree. Okay, so that's all recursive stuff. And remember that the breadth first one requires a queue and is not recursive. So yeah, just remember that pre-orders, you visit the root first, then the left subtree, then the right subtree. In order is visit the left subtree, visit the root, visit the right subtree. And post order is visit the left subtree, visit the right subtree, visit the root. So post, in, and pre, they're all talking about when am I visiting the root. If it's pre, it's first. If it's post, it's last. If it's in the middle. Okay. So now let's search for something in a list recursively. And the idea is, well, again, we can say, okay, is it in the rest of the list? Because that's your recursive call. Is your 3 there? Yes, it is. It'll return true there. And that almost checks the entire list. Recursion guarantees it'll check the rest of the list. Your job is to build up the final answer correctly by considering the extra node that you haven't looked at, that the recursion hasn't looked at yet. Okay? So here we go. Let's search for, so I've made 1, 2, 3, and they're now 4, 5, and 6, right? Or 2, 3, and 4. So let's search for like 4 and 2 to hit all the cases. 2 and then 5. One that's not there. Okay, and let's be like data. And this one will be null, so we won't print it out. Okay, so essentially this is all the same stuff. Recursively search through list. This is going to be recursively given the front of the list that we want to search through. Okay? And we're searching for an int x, for example. And this could, of course, potentially be a sublist, because we're going to pass along recursively the rest of the list when we call this inside of itself. So again, the base case is we got all the way down to an empty list, and anything that we're looking for is never going to be there. Otherwise, recursive case, search the rest of the list, and then also consider the root. Or, sorry, not the root, but the front. If it's not in the rest of the list, search your front. So return, well, it's either in the rest of the list, so recursively search the rest of the list, return true or false if you find it. So it's going to give this second list now because this is going to be first for that recursive call. You see that? Search for the same x. Either it's there or it's the root. In one of the two cases, we would have found it. Okay? So hopefully you understand why it's doing this and why it's implemented like this. Please yell at me in office hours if it's not making sense. Oops. What have I done? Oh, sorry. I guess I want to give back the pointer. Excuse me. It's been a long video. Sorry about this. Return a pointer to the node if we find it. So maybe you can edit things. So this will be null pointer. And otherwise, now we can't be so fancy. We can't be so sly. So we need to look in the empty list case. Sorry, we need to look in the sublist. And we'll eventually use that. You can do this in either order. It's slightly more efficient to always check your first node. So if you find it in the first node, you can be like, okay, I return the first node, because that's where it is. Else, you can say, did you find it in the sublist? You can search for it there. I guess technically we can return that result. Okay, so this is the idea. Either you found it in the front of the list, or you need to recursively search the rest of the list. And that's guaranteed to return a real pointer if it finds it, because that's the magic of recursion, or null pointer if not. Okay, so that is the recursive case. It's slightly fancier because I actually want to return the node this time. Okay. In theory that'll compile, and in theory it'll do the right thing. So it finds the 4, it finds the 2, and it gives back null, the null pointer, for the last thing. Okay. That's beautiful. One last example. That's all I've got for you. Recursively delete a list now. So the idea is, again, we can recursively take a list and say goodbye to it. So the smaller list, you can recursively call your delete function on it, and you can assume that it's going to correctly delete that smaller list, so long as you correctly delete the bigger list. So you have to worry about the one node that hasn't been deleted in the recursive case, which is your first node, your front, your head, whatever you want to call it. And then the base case is, again, I have an empty list that I want to delete. There's nothing to delete. Okay, if first is null pointer, return, otherwise, delete rest of the list. Get to assume that it's going to do it properly because of recursion. And then we need to worry about deleting the bigger list, deleting our root. And by root, I mean first. Okay, so that's the recursive case. That's the base case. Okay, and this will run, and you can run this through Valgrind if you want to confirm that it did the right thing. And yeah, it doesn't have a seg fault, so I am pretty happy with that. So that is all the stuff that I wrote down on our lists that we're going to talk about on the midterm. So if I load this up very quickly, I have covered pretty much all of these topics that we talked about. There's a lot. I realize that. This is only a 75-minute exam, though, so hit harder the things that don't make the most sense to you. Come to office hours. Obviously, I'm here to help you. I recorded a long video just for you, so please take advantage of me, Piazza, and office hours, and yeah, this video. So good luck with your studying, and I will see you later.